Hey, what's up everybody, and welcome back to another problem in this series on the binary search pattern. In this section, we're going to be working with this problem here. As usual, the problem can be found by filtering the Leetcode patterns list using the binary search pattern as the filter. Now, this problem is a bit tricky to understand, and I've seen many YouTube videos where the creator attempts to explain how the solution to this problem works without fully understanding the solution themselves, therefore resulting in more confusion. And yeah, I won't do that. So the problem goes on to explain the properties of a mountain array here. And essentially what all of this is saying is that a mountain array is an array that contains a peak value that is greater than every value to its right, as well as every value to its left. It's also saying that every value to the right of the peak will be less than the value to its left, and every value to the left of the peak will be less than the value to its right. In other words, the values to the left of the peak will be in ascending order, and the values to the right of the peak will be in descending order. So of course the noob solution to solving this in O of n time would just be to iterate through the array in a linear fashion, and just keep track of the maximum value, and by the end of the loop you'll have your peak. But that isn't the solution that makes use of binary search, and that solution is O of n as opposed to O log n. So we're going to go with the binary search solution. And at this point you're probably thinking, "Excuse me, good sir, how can we use binary search on this type of array if it isn't sorted?" And to that I say the key to understanding how this problem works is to understand that the array as a whole isn't sorted. But on either side of the peak, the array is sorted in either ascending or descending order. So let's go ahead and visualize this array as a mountain. As you can see, starting from the 0th index of the array, moving towards the peak, we're climbing up. That is, from the leftmost index of the array to the peak, the values are ascending upwards. And you can also see that starting from our peak, moving towards the end of the rightmost value of our array, we are moving down. That is, from the peak to the rightmost index of the array, the values are descending downwards. And descending downwards sounds a bit redundant, so yeah. If we look at both slopes of this mountain as being two separate arrays, we are left with two sorted arrays. And even though these aren't actually two separate arrays, from the perspective of our midpoint, they'll seem like two separate arrays, which I'll get into now. So how does binary search work for this? Let's first step through how this works, and I'll try to explain further afterwards because I think you need to see what it looks like first. We're of course going to make use of two pointers. Yes, two pointers, the most useful pattern in existence. So if you haven't already checked out my two pointers videos from the beginning of this course, I strongly suggest that you do so. Anyways, each pointer is going to start at opposite ends of the array. And we're going to move these pointers based on which side of the mountain our midpoint lands on. So the first time we calculate our mid, it will land on index 6 with the value being 69. And I can assure you I didn't do that on purpose. And at this point we can see that the value to the right of our mid is greater than our mid, and with this information we can conclude two things. One is that we're on the ascending slope of our mountain, because if we were on the descending side, anything to the right of our mid would be less than our mid. But in this case, the value to the right of our mid is greater than our mid, which tells us that the slope is ascending. And secondly, we can conclude that our peak is going to be to the right of our mid because our peak is going to be the greatest value in our array. So if the value to the right of our midpoint is greater than our midpoint, we know that our current midpoint couldn't possibly be our peak. Therefore, we can reduce our search area and completely ignore anything to the left of our mid, including our mid. So we move our left pointer to mid plus 1. At this point, our left is at index 7, which also happens to be our peak, but we actually don't know that this is our peak at this point because there could be a value to the right of this value that is greater than this value. We can only be certain that a value is our peak when both the left and the right pointers meet or are equal to one another. This is because we know for a fact that anything behind our right pointer is less than our right pointer's value, because when we determine that the mid is on the right slope of the mountain, we do that by checking to see if its rightmost value is less than itself. And at that point, we know that everything to the right of it is less than itself because it is a descending ordered slope. And at that point is when we move the right pointer up to the mid position, essentially ruling out anything behind the right pointer as being less than the value at its current position. And the same thing goes for the left pointer. When we move it up to mid plus 1, at that point we're certain that anything behind it is a lower value due to the left slope being ascending. So once both left and right pointers meet, everything behind both of them is less than the current point at which they sit, and that point is our peak. So moving on, we once again need to calculate our mid. So our new mid would be index 9 with a value of 79. Now at this point, our mid's value is greater than the value immediately to its right, which tells us that we are on the descending side of the mountain. That means that our peak must either be at our mid or to the left of our mid, because in a descending array, anything on the right side is going to be less than the current value, and our peak can't be less than any other value in the array. So we move our right pointer to mid. It's important to note that on the right side of the mountain, we don't move our right pointer to mid minus 1, similar to how we moved the left pointer to mid plus 1 on the left side of the mountain. This is because on the left side of the mountain, we know that the value to the right of our mid is greater than the midpoint, so we know that the peak can't be mid. But when we're on the right side of the mountain, we don't have that luxury. That's because we only checked the value to the right of our mid to determine what side of the mountain we're on. So we actually don't know if the value to the left of our mid is greater than or less than our mid. So for this reason, we just move our right pointer to mid, because in this case, our mid could potentially be the peak because we don't know if there's a greater value to its left or not. And then once again, we calculate our mid, which results in the mid being index 8 with a value of 99. And this value is greater than its right value, so we are still on the descending side of the mountain. So we move our right pointer up to index 8. And then we calculate our mid one last time, which results in an index of 7. So our mid would move to index 7. And the value at index 7, which is 100, is greater than the value to its right. So we are still considered to be on the right side of the mountain. So we move our right pointer to this index as well. And at this point, both our left pointer and our right pointer are equal, which means that both pointers are sitting on our peak. So we just return either one of these pointers as the answer to the problem. Now, let's talk about the difference between the way we usually would use binary search to search for a target value and the way that it is being used in this problem. Usually, when searching for a target value in a sorted array, we compare our midpoint to some target that may or may not be present at a place in the array. In this case, the entire array needs to be sorted because we're banking on the target being somewhere on the right side of our mid if greater than our mid, or somewhere on the left side of our mid if less than our mid. That means in either of the above conditions, we are reducing our search area by doing away with an entire side either left or right of the array. And we can bank on that because we know that in a fully sorted array, any value to the right of our mid will be greater than, and any value to the left of our mid will be less than. That means that if halfway through one of the sides of the array, the numbers go from ascending to descending or vice versa like they do in this problem, the above no longer holds true. Therefore, our original binary search algorithm can no longer work. But we can actually adjust binary search to work for this problem as well. We just need to think about it differently. For this problem, we're banking on our peak being on or somewhere to the left of our mid if our mid lands on the right side of the mountain, or somewhere to the right of our mid if our mid lands on the left side of the mountain. And we're doing that by breaking off the lesser values up to our mid on either side of the mountain. And that's actually the key to understanding how we can apply binary search to this problem. We're only breaking off the parts of our array that are less than mid up until mid on each side of the mountain. So instead of dividing our search area by breaking off an end at one extreme or one side, we're dividing our search area by breaking off pieces from both sides, zeroing in on the center or the peak. And with that being the case, a comparison of the mid and its right value can only ever result in the removal of a piece of its current slope, either the ascending slope or descending slope of the mountain. And this is why we can use binary search for this problem even though the array isn't sorted. because we're essentially isolating the reduction of our search area to the side of the mountain that our mid is on, and each individual side of the mountain in isolation from the other is in fact sorted. So this problem is actually quite confusing because we tend to be stuck in the thought pattern of traditional binary search. So it's hard to change your thought pattern to comprehend this problem in particular, but if you keep at it and maybe rewatch this video a couple of times, you'll start to see what I mean. And one last thing before we get into writing some code, the solution for this problem is actually quite useful because it can literally be copied and pasted into the solution for a medium problem called find peak element. In that problem, you're given an input array with potentially multiple mountains, but you can return any of the peaks within the array. And a little bit of homework for those of you that are A+ students, can you figure out why this same algorithm works if the array contains multiple mountains? Just don't forget to change the method name when copying the solution over to that problem. Anyways, without further delay, let's get into writing some code. Okay, so starting in our Python source coding interview patterns directory, we're going to make another directory that we're going to call peak index in mountain array. And we'll just change directory into that directory. And within here, we'll just create our virtual environment and go ahead and activate it. And then we'll create a file called peak index in mountain array.py. And we'll just open up that file. And in here, we're going to start with defining a function called peak index in mountain array. And it's going to take in an array, and that's it. And we're going to start by creating 2 pointers similar to our last binary search solution. So we're going to create a left pointer that's going to start off at the first index of our input array, and a right pointer that's going to start at the end of our array. And what we want to do is we want to iterate through a while loop while left is less than right. And it's not less than or equal to in this case, it's less than, because we want to stop the loop once both our left and right pointer reach our peak. And you'll understand more about what I mean by that when we get into the visualization. But for now, we're just going to start this while loop and we're going to calculate our mid as usual. And then we're going to check to see if our mid is less than our mid plus 1. And essentially with this mountain array, anything to the left of mid is going to be ascending. The values are going to be in ascending order from the first index, the 0th index, up to midpoint. And then anything to the right of our midpoint are going to be in essentially descending order. So from the midpoint down to the end of the array, the values are going to be descending. And again, it's going to be hard to visualize this right now, but just bear with me. But in this case, that means that we're going to need to set our left equal to mid plus 1, because if the midpoint is less than the mid plus 1, that means that we want to move our left pointer up the mountain towards the peak. So we're going to set left equal to mid plus 1. And the other case is when mid is greater than our array mid plus 1. And if this is the case, this means that our array mid is on the right side of our peak, because the values on the right side of our peak are going to be descending. So if the mid is greater than the value to the right of it, that means that the side of the array that we're on is descending, because if it was ascending, the opposite would be the case. And again, this is going to be really hard to visualize without me drawing anything out, so just try to bear with me. So, and also this elif could just be an else statement, but I just wrote elif because I want to be explicit so that you guys can understand what's going on here. But anyways, if this is the case, if we are on the right side of our array or the right side of the peak, then we're going to set our right equal to mid. So we're going to move our right pointer up the mountain towards the peak. But the reason we're not setting this equal to like mid minus 1 or something like that is because if array mid is greater than mid plus 1, we have no way of knowing if array mid is the peak or not. So we need to keep the mid in our search area because we want to make sure the mid isn't actually our peak. But that doesn't necessarily matter here because we can see that array mid plus 1 is greater than mid, which means mid can't be our peak because there's a value greater than it. So here we're able to do mid plus 1, but here we cannot. And that's pretty much it for the algorithm. And we can just go ahead and return either left or right. It doesn't matter because both left and right reach the peak by the time this while loop ends. And the way that I'm going to show you guys it in the visualization will hopefully help you guys to understand. I'm going to try to use some illustrations to help you guys see what's actually happening here, because this one can be a little bit confusing. So once that's done, we can go ahead and create our entry point. If name equals main, we'll go ahead and print the result of peak, index, and mountain array, and we're going to pass the array from the problem description. So we'll just go ahead and pass in this one because this is the one that we're going to use in the visualization as well. And the output should be index 2. So the peak here is 100. And as you can see, 100 is the peak and anything to the right of 100 is descending. So 99, 79, 78 down to 19. But anything on the left side of the array is ascending. So 24 to 69 to 100. So that's what I mean when I say the left side of our peak is going to be ascending and the right side is going to be descending. So we can go ahead and paste that in here. Let's format first, and then we can go ahead and save. And let's clear, and then just run Python 3 peak index and mountain array.py. And as you can see, we get the index 2 as expected. Now let's get into the visualization. And if you got confused with the coding section, don't worry, I'll try to make it clear for you in the visualization. Okay, so we can start by drawing out the array in our problem description. So this array is, I think, the third example array input in the problem description. And they're referring to the array input as a mountain array. And the reason they're referring to it as a mountain array is because we can visualize this array as a mountain. So we can visualize it as a mountain like so. So we can go ahead and draw out a mountain. And our peak 100, which is this value here, would be at the peak of our mountain. And then we can write out the rest of the values as well. So 24, 69, 99, 79, 78, 67, 36, 26, and 19. So here is our peak and here is our mountain. And you've probably noticed that anything to the right of our peak is descending. So 99, 79, 78 down to 19, the values are descending on this side. And anything to the left of our peak is ascending. So 24, 69, 100. So on the left side, the values are increasing, and on the right side, the values decrease. So we can go ahead and just write ascending here. And this side is descending. And let's also go ahead and write out our indexes. So we have 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9 for our indexes. So this is how we can visualize this mountain array input as an actual mountain. So you see we have the peak and we have the slopes on the side of the mountain. For this algorithm in particular, and for binary search, we're going to make use of 2 pointers. So we're going to actually be using the 2-pointer pattern as well. So we're going to set our left pointer equal to the first index of our array, and we're going to set our right pointer equal to the last index of our array. And what we're going to do is we're just going to visualize these 2 pointers as people climbing to the peak of the mountain. So we'll just go ahead and write out left here. And we'll draw a little person. And we can just move that here. And we can do the same for right. And we'll just draw a little person here. And we'll put this guy over here. So the objective is for these two people to reach the peak of our mountain. So while left is less than right, then we're going to execute the code in here, which is going to result in both of these people moving up towards the peak of the mountain. And once both of them reach our peak, the while loop's going to end. Once left is less than right, the while loop will end. That means that both of them are equal. And when they're equal, they will have reached the peak, and you'll see soon. So in that case, we can just return left or right. We're returning left here, but it doesn't matter which one you return actually. So what we start by doing is we start by calculating our midpoint. So the midpoint is left plus right divided by 2. So our left index is 0, our right index is 9. So 9 divided by 2 is 4.5, but we're going to floor it, so it's just going to be 4. So our midpoint is going to be index 4. So let's go ahead and write out mid, and we'll put it at index 4. And what we're going to do is, in these two if conditions here, we're going to check to see if our midpoint is either on our ascending left slope or our descending right slope. And the way that we're able to do that is we're going to check to see if our midpoint value is less than array mid plus 1. So if our midpoint value is less than our midpoint value plus 1, so for example, if we're here, the value 24 is less than the value plus 1. So say for example, this was our mid. If this was our mid, mid plus 1 would be 69. So we would check to see if array mid is less than 69, if 24 is less than 69. If that's the case, then that means we're on the left side of our peak. And that's because all of the values to the left of our peak are ascending, and all the values to the right of our peak are descending. So if this condition is true, it means our midpoint is on this side. But if this condition is true, if our midpoint is greater than array mid plus 1, then it means we're on the right side of our peak. And that's because the values are descending. So our midpoint is here now. So the value for mid is 79. And the value for mid plus 1 would need to be to the right of 79. And anything to the right of 79 is going to be greater because this is descending. And anything to the right of 79 is going to be smaller because this is descending. So we're checking to see if the midpoint is greater than its right value. So our midpoint is greater than our right value. So that means we're on the left side of our mountain, the descending side. And if this case were true, it would mean that we're on this side. So right now we're on this side, the midpoint is here. And if that's the case, we're going to move this guy up to our midpoint. So this guy is going to climb up towards the peak. So we're going to set right equal to mid. So we can set right equal to mid, and we'd end up back at the top of our while loop here, and left is still less than right because neither one of these guys have reached the peak yet. So in this case, we're just going to reset our mid. So our mid is going to be equal to left plus right divided by 2. Left is 0, right is 4, 4 divided by 2, or 0 plus 4 is 4, divided by 2 is 2. So that means we can move our midpoint here to 2. And now once again, we arrive at this line. We check to see if our mid value is less than our mid value plus 1. So is our mid value less than the mid value plus 1? No, it's greater than still. That means we do this line of code. So we're going to set our right equal to mid. So we'll move our right guy to mid. So our right guy has actually reached the peak, but our left guy hasn't yet. So we'll go back to the top of this while loop, and left is still less than right, and we'll recalculate our mid again. So now we get our midpoint by adding the index 2 to 0 divided by 1, which equals index 1. So our midpoint becomes index 1. And as you notice, our midpoint is now on the left slope. So this condition is going to be true now, because if our midpoint is less than midpoint plus 1, so our midpoint is less than its right value. So that means that we're on the ascending side of the mountain. And if we're on the ascending side of the mountain, what do we need to do? We need to make our left guy climb up to where the midpoint is plus 1. So this guy is going to climb up to midpoint plus 1. So this is going to actually bring him all the way to the peak. And the mid we're not using anymore. So at this point, both of our guys are at the peak. So when we get to this condition here for the while loop, we're going to see if left is less than right. But in this case, left is now equal to right. And that means that both of our guys are at the peak. And that means that we can just return either one of those because that's the peak index. And as you may have noticed, just now when we had our left at index 0, and we had our mid at index 1, we were able to move him past our mid up to the peak. So we were able to move him to mid plus 1. And that's because in this condition, if our midpoint is less than its right value, that means that our midpoint can't possibly be the peak because there's a value that's greater than it. So that means that we're able to move this guy to mid plus 1. But in the case of the right side, so if our guy is here and our midpoint is this index, and here we check to see if our midpoint is greater than mid plus 1. If this condition resolves to true, then we can't set this right to mid plus 1. We have to set it to mid because we still don't know if this value is the peak. So for example, let's go ahead and just move him down. And let's make the mid the peak for now. So with the mid being the peak here, this condition would resolve to true if mid is greater than array mid plus 1. So the peak here is greater than this value here still. But if we were to do mid plus 1 here, this guy would move to mid plus 1. He would move past our peak. And that's not what we want. We want him to move to the peak. So that's why in this situation we're able to set it to mid plus 1, but in this situation we can't. So that's going to be it for the solution, the explanation of the algorithm. So now let's get into time and space complexity, starting with our time. And of course, our time is going to be O of log n. And that's because this is a binary search solution. And as for our space, we're not using any space or any extra space. So the space complexity is just O of 1. We're not using a recursive binary search solution. This is an iterative solution. So we're not using any stack space or any extra stack space. So our space complexity is O of 1. And that's going to be it for this problem, and I'll see you in the next one.